Good afternoon. My name is Caio and I will present the paper A Statistical Approach to Predict Operating System Failures based on Multiple Failures Association. There is no doubt that computer systems have become one of the most important tools in modern society, and based on previous studies, we know that failures in these computing systems are mainly caused by software defects, and these defects may lead to simple inconvenience to risking human lives. Moreover, reliability is a major concern not only for critical systems, but also for commercial off-the-shelf software. For example, the US Navy navigation systems run on top of regular Windows operating systems, so the OS layer should guarantee at least the same level of reliability expected for the user applications. Note that in most computing systems, the software layer is divided into applications and the operating system. But given that user applications depend on the operating system, there is no point in having highly reliable applications if the OS doesn't have an equivalent reliability. Therefore, the motivation for conducting this research comes from the importance of OS reliability for computing systems and the lack of research in this area. In our earlier papers, we analyzed OS failure occurrences in real working environments, and we found empirical evidence of patterns of multiple event failures occurring within well-established time intervals, which suggested the existence of underlying mechanisms governing these OS failure behaviors. The results from our earlier studies motivated this research, in which we propose a generic statistical approach to predict OS failures based on associations. We compute the probability of a given failure to occur within a time interval upon the occurrence of a particular pattern of preceding failures. This analysis is essential towards more effective and accurate reliability approaches. For example, if a system knows that there is an 88% chance of occurring a failure B after a failure A, the next time failure A is observed, the system can perform proactive actions to prevent future failures. We used a commercial off-the-shelf operating system software as our research subject, the Microsoft Windows 7, which is still one of the most used desktop operating systems. Moreover, Windows 7 provides detailed failure registries through its reliability analysis component, also known as RAC. The RAC collects some information about the failures and stores it in these fields, like the computer name and the time when the failure occurred. These 5 highlighted fields are the main fields we used in this research, and they were used to uniquely identify each failure event. Our work sample comprised 7,007 failures obtained from 566 computers running Microsoft Windows 7. The data were organized into 4 groups. G1 and G2 are from the same university. G1 comprehends failures in computers of undergraduate teaching laboratories, and G2 are from the university's administrative departments. G3 contains failures in computers of a corporate environment, and G4 is a heterogeneous group and contains failures in computers from different environments, such as household, corporate, and academic, among others. Some previous works have investigated the reliability of operating systems. However, all of them considered as OS failures only the failures that occurred in the kernel space. But we know from the OS theory and practice that modern operating systems have several of their parts executing in both kernel and user spaces. Therefore, we adopted an approach introduced in this 2013 paper from our research group to categorize OS failures that occurred in both kernel and user spaces. So, based on the fields event identifier, product name, and source name of the RAC record, we classified each OS failure into one of these 3 categories. The OS application category contains OS application processes failures. These application processes run in user space, and one example is the explorer.exe. The OS service contains OS service components failures. These service components also run in the user space, and one example is the Internet Explorer update. And finally, the OS kernel contains OS kernel subsystems failures. These subsystems run in the kernel space, and one example is the video DDR error, which is a display driver failure. Note that the most common OS failures belong to the OS service category, with 60.63% of the failures. Since OS service contains the highest percentage in failure events, we analyzed the field source name in the failure records of this category, and we found that 23 types of OS service failures were related to software updates performed by the Windows Update Service, which is the standard software update mechanism in Windows 7. These 23 types corresponded to 87.97% of the total number of failures in the OS service category. Given the prevalence of OS failures related to software updates, they were clustered into 23 subtypes within the type Windows Update Service. An analysis of these 23 subtypes showed that only 4 subtypes represented most of these failures, which are Internet Explorer Update, Windows Update, .NET Framework Update, and Office Update. This is an overview of the OS failure stratification. We first divided the OS failures into categories, then into types, and for the Windows Update Service type, we created subtypes. In this paper, we considered as association a systematic relationship between an OS failure with other preceding OS failure. And to discover these associations, we begin by verifying if the last failure of a computer's log, for example failure D, has a preceding failure that occurred on the same day or on the previous day. If so, we fill out 2 additional fields we created to store information about the previous failure and the delta t between them. And we follow the same logic for the other failures. Note that failure B doesn't have a previous failure, since failure A occurred 2 days apart, and failure A also doesn't have a previous failure, because it is the first failure of the log. Note that we analyzed failure associations between 2 days to encompass cases in which failures occurred in computers running overnight. However, this could create unrealistic associations. For example, if the first failure of a computer occurs in the morning of one day and the second in the evening of the next day. To tackle this problem, we get all occurrences of an association, for example, the association between failures C and D, and we calculate the confidence interval around the median of their delta t's. Finally, we select only the occurrences with delta t less or equal to the upper bound of the confidence interval, which also guarantees that the association is consistent within that time interval. In addition, we choose only associations that happen in at least 3 out of the 4 groups of the sample, since we are interested in consistent associations that occurred in multiple groups. Following, we added the associations as input to the multinomial logistic regression, in which the first failure on the association represents the possible values for the independent variable, and the second, the possible values for the dependent variable. Finally, based on the regression models, we can calculate the probabilities for all combinations of values between the dependent and independent variables. So, one of our main goals is to predict the probabilities of a given failure to occur upon the occurrence of a particular pattern of preceding failures. We used 2 approaches to compute our model's goodness of fit. The first is the McFadden's R2, and the second, we analyzed the model's prediction accuracy. And to do that, we randomly split the data between training and test, and we generated the models based on the training data, and we tested their accuracy using the test data, which contains unseen data. Now I will present our main results. In our prediction approach, we looked for patterns of three types of failure associations: associations between categories, subtypes, and subtypes with the delta t between them. For the associations between categories, both dependent and independent variables are OS failure categories. In this case, we observed a very good fit for the multinomial logistic regression models, and we could predict more than 95% of the occurrences. Moreover, we observed that there is a high probability of occurring associations between failures of the same categories. We observed that the most frequent associations were composed of OS service failures, especially Windows Update Service, and we found that only 4 Windows Update Service subtypes compose more than 90% of these associations. Therefore, we performed a new prediction based on these associations. In this case, both dependent and independent variables are Windows Update Service subtypes of failures. Once again, the models had a very good fit, and we could predict more than 80% of the occurrences. We observed that there is a higher probability of occurring associations with the same subtype, but there is also a significant probability of occurring Windows Update failures after most of the other subtypes, which is highlighted in dark green. One important property that contributes to a better understanding of the OS failure associations is their delta t values, so they were added as independent variables in the models. We had to divide the delta t's into categories by computing the minimum, maximum, and quartiles of their values, and each statistic represented a delta t category. Finally, we added the delta t's into the prediction approach as a second independent variable in the previous model. However, the accuracy didn't improve much in comparison to the past model, but using the delta t allowed us to uncover new other failure association patterns. For example, there is a significantly higher probability of occurring Windows Update failures within small delta t's with respect to any other subtype that occurred before. Prior to this study, we didn't know the answer to questions such as: could we use patterns of failures association to predict OS failures? And if so, at what level of accuracy? And is it feasible to implement the results as a part of an online OS failure prediction system? In response to these questions, our prediction approach was able to predict OS failures with good to high accuracy, and the empirical evidence observed suggests the feasibility of using our approach to implement online OS failure prediction, which must be composed of two main tasks: the continuous calibration of the model's coefficients with new incoming failure records, and performing the probability estimation of the next failures to occur, as well as the appropriate preventive actions based on these outputs. Thank you.